Hi, I'm Başak Falay. I will present how did we couple the physical and machine learning models with a case study. The pure white box models can have time-consuming development and validation problems. The black box approaches that examine the system from the outside uses this input and output relationships and can have advantage when the detailed information of the component is not known. And we thought it would be fun if we would like to try and see the limitations and opportunities to combine these two modeling approaches. First, I would like to give an overview of the workflow. The physical models were implemented in Modelica language, and the Daimler 2021 was used to simulate these models, and you can see this icon. And the machine learning models is implemented in Python by using the sklearn library. And our aim is coupling these models. And therefore, we have deployed a tool called UniFMU. Many of us has virtual environments in Python to avoid the conflicts of the libraries. And when we want to couple the physical models with the machine learning models, we require Dockerized FMUs. And the process of creating this Dockerized FMUs using the UniFMU tool will be also detailedly covered today in a session by my colleague, Thomas Schanz. So I don't want to steal the show. The FMUs generated with the UniFMU required Python during the runtime because our machine learning models is implemented in the Python environment. What is basically we are doing is we train the machine learning model. This pre-trained model saves the parameters as JSON and the model as pickles. And we read the files at the beginning of the simulation. And in every due step, the model does the prediction of the target values using the loaded models. And now I would like to show the application of the workflow in a single family house, which is located in Styria, Austria. The figures in here shows the overview of the main components of this single family house heating system. Let me introduce this control strategy quickly. The priority of the solid collector is to maintain the temperature of the top layer of the storage tank at 52 degrees. If this condition is satisfied, then the excess heat from the solid collector heats the pool to 35, indoor pool to 35 degrees. If the solid collector cannot meet the demand of indoor heating pool, and if the top layer of the temperature of the storage tank is higher than 52, then the storage tank heats the pool. If this condition don't satisfy, and if the bottom temperature of the storage tank is less than 35 degrees, then the heat pumps turns on. If the temperature of the stove, which is heating the room, is higher than 40 degrees, the excess heat is fed to the storage tank. All the models used in the system are based on the Modelica Ellipse Project 1 and Buildings Library. The energy demand of the house from the floor heating and the heat supply profile of the stove were taken from the measurement data instead of modeling these components because it was too complicated. Since there was no weather profile acquired within the given data period, typical meteorological year for Styria, Austria was generated from the meteonorm to be used for the solid collector. And there was no available information of the system parameters of the storage tanks, such as the insulation material, thickness, wall thickness, height, or the location of the temperature sensors. Therefore, we see this opportunity to model the storage tank based on the machine learning, which is implemented in Python. Before introducing the machine learning model, I would like to talk about the measurement data first. What we have as a measurement is the data from the February 2019 till January. And on the left-hand side, you can see that the white lines represent the missing data points of the given period. And what we have done is we imputed these missing data points by taking the profile of the previous day for each label. So what does it mean? Is basically, if we check the temperature of the storage tank, you can see in the September, the 4 days, we didn't have any data. So we basically take the previous day profile and paste it to these missing points. The dashed line represented that way. And by the way, after November, we assumed that the heat meters were broken or there was something wrong because there were so many missing data and the one we have was not really proper. So we have to ignore this part. At the end of the pre-processing, we are left from February till November, the data period, and we have resampled our data set to 15 minutes interval. We have used the random forest model, which predicts the 4 temperature layers of the storage tank. An overview of the input of the model is given here. The static features are the temperature and the mass flow rates of each heating models, solar, heat pump, stove. And additional to them, we have introduced something called P-load, which indicates whether at least one of the components in the system is on and the room temperature where our storage tank is located. Additional to the static features, we have dynamic features of the storage tank, which all the 4 temperature layers, which with the 1 hour look back with 15 minutes interval and a 15 minutes prediction horizon. One of the most critical features in this dataset was the mass flow rate from each component. So on the right-hand side, we try to illustrate the sparsity of the mass flow rates for each component. And the y-axis represents the data points, which is 27,840 data points, and the x-axis shows the component's mass flow rate. And you can see the black dots represent the values that are not 0, and the gap represent the values that are 0. So from here, we can see that the stove component has the highest 0 values with 99.8%, and the collector to pool is 86%. To evaluate the performance of our model, the coefficient of variation of the root mean square and the mean absolute percentage error for these 4 temperature values are given in the table. The 3rd and the 4th temperatures are the worst predicted target according to these metrics, which I thought the best way to elaborate this table is to support the result with some figures. Therefore, the machine learning model is imported as FMU in Daimler and testing the FMU machine learning model with the measurement data. We decided to test it, and we had 3 different periods, winter, spring, and summer, in order to aim the different boundary condition. I will quickly talk about these 3 periods. I think I don't have enough time. All these figures, the first subplot represent the temperature values of the tank, and the second is the mass flow rate, which you can also interpret it as the on and off situation of which component is. In the summer, frequently running components are the collector and the pool. And based on this component input, our model predicted values shows a good agreement with the measurement data during the summer period. And what we can see that introducing this P-load feature, that we could capture the cooling behavior of tank during the night when there's no load situation is on. However, in the spring, there are more components interacting with another. From the measurement data, we have figured out the cold return water from the floor heating is fed to the storage tank from the bottom and the middle layer. And therefore, the bottom and the middle cyan and the dark blue supposed to decrease from, as you can see from dashed lines. However, between the 19 and the 18, when the floor heating is on, the green curve, that we see our predicted values, temperature values are not capturing this behavior. And in the winter period, again, when there's this floor heating, this time we could capture the cooling behavior. However, when the heat pump is on due to the control strategies, where the blue curve is supposed to increase, which the warm water is fed to the middle layer, we cannot capture this. And what we have learned from here, the temperature values of the storage tank is predicted better when there are only collected components on, which is the summer period. And we came up with the data that represent the collector to storage or the collector to pool is denser than the other components data. Therefore, the static features dominate the prediction more than the other static features, which are sparse. And we have mentioned from the metrics that the 4th and the 3rd layer of the temperature was the worst metrics because the floor heating and heat pumps are the one that changed this temperature distribution. And again, we think that due to the sparse data, the prediction of these layers are not reliable. Additional to the static features, the dynamic features, which is the past prediction temperature values of the storage tank, are as well as an input feature. And once these values are predicted wrong, the error accumulates to the further steps. However, we were not really pessimistic. So after all this lesson learned, we were still curious about coupling the components in the system simulation. And we would like to see the simulation result, the simulation time, and you can see the configuration of the whole system simulation is given in the figure. And from our result, we can see the temperature of the all storage temperature layers and the controls of the all, which components is on, which is off, and again, this preload condition. Despite the same real-world control strategies implemented in the system, the weather profile that represent the measurement data was not available. Therefore, as I mentioned, the profile is generated from the meteor norm and used for the solar collector. And of course, our solar collector output and all other control strategies are not exactly the same with the measurement data. Therefore, we cannot compare this result with the real-world system measurement data. What we could have done, we could have modeled the storage tank based on the physical model, but we haven't calibrated the model based on the measurement data, which not yet. This is what we would like to check later. What I can tell from the simulation is we have done 10 times the same simulation and take the average, and 32 days of simulation takes 4 minutes. What are we still curious for? As I said, these were the preliminary result. We are still curious about the co-simulation environment, comparing the simulation time with the co-simulation physical model versus co-simulation machine learning model. Once we calibrate the storage tank physical model, we would like to compare the result, and we would like to deploy different machine learning models for the storage tank. That was my last presentation. I will be looking for the questions.